Next, let us count integer compositions. What is an integer composition? A composition or integer composition. We are going to say composition without the integer, but there's other kinds of compositions too. So this has nothing to do with the composition of functions. So a composition is a tuple that is a finite list of positive integers and ordered list. Generally, when I say list, I mean ordered list. Furthermore, let n and n. A composition of n means a tuple of positive integers whose sum is n. For example, what are the compositions of 3? One of them is, this is the simplest one, this is just 3. It's a one tuple that contains only 3. The sum of the single number 3 is 3, so it's a composition. This is perhaps more interesting. It's a pair of 2 and 1, and their sum is 3. Next, 1 and 2. Keep in mind, it's a tuple is an ordered list, so 2 and 1 is not the same as 1 and 2. And finally, you also have 1, 1, 1. So it's 1 plus 1 plus 1 is also 3. So in other words, a composition of n is a way of writing n as a sum of positive integers, and the order matters, so these are not the same composition. So let's count them. Let n and n, then the number of compositions of n is, and this is strange, the number is, you have cases. So in the usual cases when n is at least 1, then the number is 2 to the n minus 1. For n equals 0, this would give you 1/2, which is not something you would expect to get in a combinatorial formula. A number should be an integer. So yes, this is not true for n equals 0. For n equals 0, you have 1. Let's prove this. Again, we're just sketching the proof. So without loss of generality, assume that n is at least 1, because the 0 case is just, you just count them. There is only the empty tuple, which gives you this 1. Now, so what do we do for n being at least 1? Here is, so it's tempting to use the bijection principle again. How can we do that? We want to define a bijection from the set of all compositions of n to some sets whose size is 2 to the n minus 1. And inspired by the theorem here, we could try and use the set of all subsets. Sorry, no bracket here. Of S, where S is the set of the first n minus 1 positive integers. If we have found such a bijection, then the previous theorem, so then we can apply the bijection principle to obtain that the number of compositions of n equals the number of subsets of S, and this is 2 to the n minus 1 by the previous theorem, since S is an n minus 1 element set. So how to find such a bijection? If A1, A2, and so on, AK is a composition of n, then consider the set of all its partial sums. So these are sums of the first I entries of this composition. I is bigger than 0 and smaller than k. So we don't take the empty sum and we don't take the sum of all the entries. So explicitly, this will be A1, A1 plus A2, A1 plus A2 plus A3, and so on. A1 plus A2 plus and so on plus AK minus 1. We don't go until the full sum. We stop at the second to last element. Claim this is a subset of S. Why Well, because we're summing at least one element, we will have positive integers everywhere here. But if you sum all elements, you have n, because it's a composition of n. Since you never sum all elements here, you're always missing out at least on the last element. You must therefore get a sum that's smaller than n, because all these a's are positive. So this is a subset of S. Moreover, the map that takes a composition to the subsets, so the map that takes A1, A2, A2 and so on, AK, and sends it to the set, is a bijection. This is not hard to check. What matters here is that this map is injective, because if you have the set, you can reconstruct the composition. You just set up the elements of the set in increasing order, and those are your partial sums. So knowing these partial sums, you can reconstruct A1. By taking the difference, you get A2. By taking this difference, you get A3, and so on, until AK minus 1. And then, because the sum of all of them is n, you can reconstruct AK as well. So indeed, it is injective because we can reconstruct the composition from the set of its partial sums. It is surjective because any subset of S can be obtained from some composition. Why? If you have a subset of S, it subdivides the set S into little intervals. And the composition, the AIs are just the sizes of these intervals from left to right. This is how you undo this map. So therefore, the bijection principle, as explained above, yields a proof of the theorem. So much for compositions in the literal sense. So let me call this map F. Here's just an example of what this F does. If n is 7, then F sends this composition 3, 1, 2, 1 to the set 3, 3 plus 1, 3 plus 1 plus 2. So 3, 4, 6. And if you have 3, 4, 6 and you want to reconstruct the composition, you look at the differences between consecutive elements here. So 4 minus 3 is 1, 6 minus 4 is 2, and finally the last one is what you're missing to get 7 as a sum. So this is how you undo this map F. So much for just counting all the compositions.